Hello, everyone. Hello, everyone. I welcome you to. Hello, everyone. I welcome you to this tutorial session on smart grid basics to advanced technologies. Before I start the session, I would like to introduce myself. I am Mohd the Prime Minister Research Fellow of Department of Electrical Engineering. I will be taking this course. In this course, what I'm going to do here is first of all, first of all, I will be, you know, recapping the recap of the whole week course which you have just learned in the last week. Then I will solve some questions regarding this topic. So I would like to now start the session. So in this week, what I would like to introduce here is regarding the energy management. Energy management. Okay, I would like to introduce this topic here. So, what does energy management do? Just a second. Okay, what does energy management do? Energy management is actually a technique to manage the energy in our grid because we have a limited amount of generations. We have limited amount of generation. So those limited amount of generation will be used to satisfy our demand. So there should not be any losses or uh, wastage of energy. So that's why the energy management is very much important. Okay, I hope audio is coming. If it not, you can write in the chat box. Okay, so let's move on to this. So why energy management is important? This just I have discussed that that we have a limited amount of energy generations, and these energy generations will be used to satisfy our demand. So the energy flow, or we can say the how the energy satisfy our demand, so that it will not lead to the wastage of energy. So that's why this topic of energy management is very much important. Now coming to why the energy management is important, there is also a reason to that, which is that energy, because generally nowadays we are moving towards the renewable based generations, renewable based generations. So like that, for example, solar, wind, biogas, or biomass. Okay, there are various fuel cells also there, battery supercapacitors. So majorly there are two major kind of these, which are solar and the wind. So what happens here is that because these renewable energy sources have their own power generation scenario, like power generation situation. Why it is like that? Because solar will generate the energy in the time when the solar uh, sun is out. Okay, then only the solar will be able to generate. Wind will generate the energy when there are heavy or high speed winds are flowing through the atmosphere, then only they can generate the energy or the demand. So, generations. But those timing of the generation of these energy sources may or may not coincide with the energy demand, may or may not coincide with the energy demand. So I will write it down here. Energy generated from renewable energy sources is dependent on the atmospheric conditions. But there may be a scenario, just a second. There may be a scenario, there may be a scenario when these generations of energy may or may not coincide with the demand. फिर क्या होगा? Like for example, there is not enough demand in the day, then what we will do, we will store that energy in the battery storage systems. So, in overall, what I want to say, explain it to here is that generally, generally there may be a situation like, for example, at any point of time, the energy is generated from solar, but at that point of time, the demand was not there. So basically, you have to manage the energy you have to manage the generation so that those generated energy should not be gone wasted. So that's why energy management, therefore, energy management is very much important. Okay. So now, in this energy management, battery, or I would say battery energy storage systems play a plays a vital role. Because if you want to, manage the energy, then somewhere down the time, somewhere at any point of time, we have to store that energy. At that storage of the energy, then those stored energy can be used for the other at the other point of time. Okay, so that's why batteries play a very pivotal role in the energy management. As you can see nowadays, there is an advent of electric vehicles. Okay, electric vehicles. Electric vehicles are also very much, they play a important, important role in the energy management, like energy management system. So, like for example, if there is, EVs are there in any system, let's say there is 1000 EVs, and what happened here is that if let's say 50% of these EVs have excess SOC, or we can say excess energy, and there is a situation in the grid that there is a peak load happening, and the energy management system allows these EVs to to send back the extra energy. How much energy will they send will be decided by the user to the grid by using vehicle to grid, or you can or V2X by any of these technology. Then what happens here is that the EV will send their excess SOC toward the grid by using vehicle to grid, and then what it will help? It will help in the load shedding. It will help in load shedding, and also actually it will help in reduction of the load shedding, and also peak load reduction. So what happens here is that the peak, the peak, the peak energy demand will be shared by conventional electric vehicles or also the battery storage system. So here, this is how, and this is a broad classification how the electric vehicle or any battery storage systems play the important roles in the energy management. Now, why these energy management is very much important? So, what happens here is that actually there are various organizations in international scenario, like Paris, which have done Paris agreements, like they have done Paris Agreement, and United Nations have set up a certain rules for for the sustainable development, for sustainable development. So what happens in these sustainable development goals, there is one which is the clean energy goal. We have to provide the clean energy and something like that. So what happens here is that in this energy, what we have to do, we have to reduce the carbon emissions. We have to reduce the carbon emissions. We have to reduce the carbon emission by using the clean energy. What are those clean energy? They are solar or wind and biomass, fuel cell, something like this. So, in order to reduce the emissions, we have to move on from the conventional, which is fossil fuel based, towards the renewable based energy sources. So that's why the emissions reduction can only happen. So, but there is a negative side of that. In the longer run, we have to satisfy the demand. But in order to satisfy the demand, we have to provide the energy demand from the renewable energy sources. But like I have just mentioned, the renewable energy sources, they are very much intermittent, and what they do, they have certain generation pattern which may or may not coincide with the load demand. So that's why the energy management is very much important, so that the wastage of energy can be reduced. What it will do, energy management, what it will do, it will reduce the wastage of energy. Second, it also helps in integration of battery energy storages. So, I would like to say not battery, more specifically solar, wind, and EVs. Also, I would say. So, it will help in this. Then, eventually, subsequently, it will lead to decarbonization of our economy. So, that's why the energy management is very much important. So, now, okay. Now, in the previous lectures, we have discussed about like various microgrids like DC microgrid, like AC microgrid. Okay, so there are various structures of those. So I will draw a DC microgrid structure where there is a utility. This is utility. It is connected through a power electronics circuitry, or I would say I have already discussed. This is full H bridge bidirectional converters. Okay, bidirectional converters. Okay, then then it is connected to a DC bus. Okay, which is, I would like to draw it here. This is DC bus. Now this DC bus, this DC bus is connected, and now the power flow will be bidirectional. Okay, let's say this is PG because it's a grid power. Either it will go into the utility or it will go toward the DC bus. Now, as we know, these solar converters are connected. This is PV panels, as they produces the DC supply, so it will be connected like through a DC-DC to control the voltage supply. This is generally a boost converter. Why? Because it will help in controlling the output. So I will write it down here is PPV. Now another here is this battery. I just told you about this. Battery is a very much important part of any energy management. This is DC to DC. Okay. This is single H bridge converter, which is bidirectional. Okay. PB. Let's say the power coming from this battery is PB. Then here is ultra capacitors. We have already talked about in detail about these ultra capacitors. These ultra capacitors have a certain advantages over the batteries because they can, due to high energy field, they can store larger amount of charge, which will lead to a higher voltage, a higher capacity. Okay, they are also connected through a DC-DC single H bridge bidirectional converters. Okay, so this is also connected, and the power flow will be bidirectional. Why? Because sometimes they will be get charged and sometimes the load will be extracted, sometimes the energy will be extracted from them. Then comes the loads. So these loads are connected through some relays for the protection scheme. Okay, let's say this is load 1, this is load 2, this is load 3. Okay, these are relay 1, relay 2, relay 3. Okay, let's say another load is here, much bigger load, load 4. This is connected through relay 4. Okay, so this is a system architecture of a DC micro grid. Now, here some of the loads will be categorized as essential load. Let's say this L4 is essential load. Okay, why this is essential? It may be a hospital load or critical care units load where you cannot you cannot remove the supply of these load. It can be done only in a emergency situations. Okay, so what happens here is that, and these all others are the non-essential loads. Okay, so what happens here in this? Now there is now a power flow control strategy is placed. Okay, what is this power control strategy? Is this, in this strategy what happens here is that there is a reference current value. Okay, एक reference current value होगी. Based on that reference current value, the operating modes of of battery and ultra capacitors will be decided. Ultra capacitors will be decided. Okay, so there will be PI controllers. Okay, which gives which gives the duty ratio uh, of what, duty ratio of the converters which are connected to battery and ultra capacitors. Now, what these duty ratio will do, these duty ratio will, you know, govern, or I would say determine the input current and input current of battery and ultra capacitors. Okay, so their inner, the control loop will of these will be like this. Like say this is a plus minus, this is I of capacitors, ultra capacitor. This is I reference. Okay. Then an signal will go into the controller. It will be passed through a limiter. Okay. Then DUC, which is the duty ratio of ultra capacitor. Okay. This duty ratio will go towards the comparator and it will give the switch a status. So this is the a inner loop control of a what is this? It is inner loop control of ultra capacitor. Okay. So similarly, this control will be carried out the same the same scheme of the control will be given to the battery. Okay. Now another control here will be for the there. Now I will draw the control loop of the PV. किस तरीके से पीवी का आउटपुट का कंट्रोल लूप बनाया जाता है तो क्या होता है पी पैनल से क्या होता है एमपीपीटी मोड पे ये काम करते हैं बिकॉज वी ऑलरेडी टॉक्ड अबाउट दैट इन द पीवी पैनल जनरली वर्क एट द एमपीपीटी मोड व्हाई बिकॉज इट विल गिव maximum power output. Okay, so the current of IPV, the voltage of VPV, then it will give VMPP. This is the reference, okay, given to this block, okay. Then another VPV and V bus, okay. There is a switch which will connect either to VPV or V bus, okay. This will given to the controller. Then in duty ratio of PV will be what is DPV? Duty ratio of the controller which is connected to the solar it will be given. Then a triangular wave is also given. It will based on that it will command the switch status. Okay, so this is the you know wo- the inner loop of the PV battery and other things. So what is there is another loop which is a GSC control loop. What it does? It actually it actually receives what it receives. It receives the reference from the power flow control strategy. Okay, PFS, and then operates accordingly and operates accordingly. Okay, then I have just discussed about the PV control loop. So what does I will write it down here. What is the status of the PV? Like I said, is always operated in the MPPT mode. Always operated in maximum power MPPT mode. Okay, this MPPT mode provides what it does provide. It provides a reference voltage which is generally tracked by voltage source. Okay, voltage source. Voltage source. And This voltage source is controlled through PI, and the output produce uh, an output is produced by the help of ड्यूटी रेशो. इसी से क्या होता है, कन्वर्टर का क्या ड्यूटी रेशियो होगा वो डिफाइन होता है. तो एक माइक्रो ग्रिड के अंदर क्या क्या कंट्रोल स्ट्रेटजीज लग रही होती हैं वो मैंने आपको बताया. ओके, there is a control strategy of ultra capacitor. Same control strategy will be given for the battery also. Okay, the control strategy for PV and then GSC. So what here is this? So अभी क्या this control strategy is done for the power flow. This is whole comes under the power flow control strategy. तो इसको लगाने का फायदा क्या होता है? What we have to do here, the main aim here is to do the peak demand reduction. Peak demand reduction. Okay. One of the major aim of this control strategy is this. Okay. Another another aim of this is to smooth transitions between different modes. So it helps in the transition of microgrid between different modes like isolated mode और a grid connected mode. Okay, इससे एक और फायदा होता है, it helps in control and management of energy. Okay, कि इट हेल्प्स इन कंट्रोल एंड मैनेजमेंट, कि मतलब कि सोलर पीवी से कितनी एनर्जी हमें मैक्सिमम आनी चाहिए और ये एनर्जी किस जगह इस्तेमाल होनी चाहिए, लाइक एसेंशियल लोड्स, नॉन एसेंशियल लोड, एक प्रायोरिटी ऑर्डर बनाया जाता है. ठीक है, और कोई बैटरी ओवर चार्ज नहीं होनी चाहिए, सो दैट द द लाइफ ऑफ द बैटरी गेट्स रिड्यूस. तो इसमें जो है सारी चीजें एनक्लोज हो जाती हैं. तो अनोदर द main aim of the peak flow strategy is also to reduce the stresses on battery. It also reduces the risk of overcharging and deep discharging. ठीक. It also helps in it also helps in helps in the helps in increasing life of storage systems. Okay, now here there is a flow chart regarding this. Okay, how this peak load is given or no, or like that. Okay, so what is that flow chart? I will show you here the flow chart regarding this. It's a quite complex flow chart, so I will not going to write it. It will be you know easy to understand it over here. सबसे पहले we will check about the we will we will check about the supply orders. Okay, फिर उसके बाद हम चेक करेंगे either you know like I will write it here. We will first check if the SOC is less than 30 or not. If it yes, then we will go towards A. If it's not, then we will check whether the PV generation is greater than P load. If it is not, yes. If it's not, then grid will supply the energy. If it yes, then again we will check whether the SOC is greater than 90 or not. If it yes, then we will go towards the strategy of load flow. Otherwise, different techniques will be applied. Okay. So I will discuss in detail the different operating modes. In those operating mode, I will cover the flowchart. Okay. Different operating modes of PFCS. Okay. So what happens here is this, as we know that our aim here is to reduce the peak demand. So there are two types of mode, which is peak hour mode. Another is off peak hour mode. Okay. So पीक आवर मोड और ऑफ पीक आवर मोड क्या होता है? पीक आवर मोड तब है जब डिमांड जो है हमारी इज वेरी मच हाई, एंड ऑफ पीक आवर मोड मीन्स व्हेन द डिमांड इज लो. इट आल्सो नोन एज वैली. ओके. एक पीक डिमांड होती है इस तरीके से, ये पीक डिमांड रीजन है, ये वैली रीजन है. ओके. तो पीक आवर मोड में क्या होता है? द प्रायोरिटी मेन एम, main objective here is to supply grid, or we should draw minimum power required for essential loads. ओके. तो पीक आवर में क्या होता है कि हम जो है मेन ऑब्जेक्टिव क्या है? आइदर वी सप्लाई टू द ग्रिड, और अगर हम ग्रिड से सप्लाई ले रहे हैं तो वी शुड सप्लाई विड्रॉ द मिनिमम पावर विच इज जनरली रिक्वायर्ड बाय द एसेंशियल लोड्स, which I just discussed. Ki there are two types of load. Essential load, which should not, the supply to them should not be removed in unless and until there is some emergency. Otherwise, non-essential loads, we can remove the supply. So when the peak hour mode occur, we should draw the minimum power, or either we supply to the grid. Okay. But in the peak hour, the cost of this energy is very much high because it is at the peak hour. Okay. But in the off peak hour, the cost of energy, or we can say cost of power, is lower. Okay. अब क्या होता है पीक आवर में? वी ऑल्सो इन पीक आवर वी ऑल्सो डिस्चार्ज आवर बैटरीज, but in off peak hour we charge our batteries. Why we charge our batteries? Because the cost of charging of our batteries is low. I have just said कि charging cost जो है इस time low होती है, cost of power is low, so it is very much essential, or we could say good, that we should charge our battery in this. But here another thing is that कि हम इतना चार्ज नहीं करें कि it will lead to another peak. एक और पीक ना बन जाए, पता चले. ओके. कि हमने ऑफ पीक आवर मोड में इतनी चार्जिंग कर ली, इतना डिमांड बढ़ा दिया कि इट क्रिएट्स अनदर पीक. तो दैट वी शुड मेक श्योर दैट एनर्जी डिमांड In the off-peak hour should not be increase increase so much that it drives the conventional generation towards another peak hour mode. Okay, what will happen? It will lead. This will lead to more carbon footprint. Okay. Okay. So now there is another mode of operation which is an isolated mode of operation. Isolated mode of operation. So in this mode of operation, so in the isolated mode of operation, what here there is the conventional grid encounters failure, or I would say any outage. इससे क्या होगा? This will disconnect the grid from the microgrid, or would say DCMG, which is DC microgrid. Okay. So what happens here is that load shedding will be done. Okay. And in this mode, generation becomes lesser than load demand. इसी वजह से तो हम लोड शेडिंग करेंगे, और लोड शेडिंग के बाद we will deliver, or we should, I would say, discharge our batteries. Okay. Okay. This will the thing. Okay. Now I would like to show you uh you know simulation results of the. Now what happens here is this simulation is carried out on a grid interactive DCMG system which is implemented in a real time digital simulator. Okay. अब क्या होता है, जो मैं हमने एक मॉडल बनाया था उसको हमने एक सिमुलेशन सॉफ्टवेयर्स में उसको कैरीड आउट करा बाय विच इज अ रियल टाइम डिजिटल सिमुलेटर, और जो एफपीएससी हमने एक्सप्लोर करी है उसको हमने इम्प्लीमेंट करा. एंड assessment of the power flow control strategy is being done in three major modes. Initially, two modes are लिए which cover peak hour and off peak hour during utility connected. फिर हमने एक मोड लिया इन एन आइलैंड. तो तीनों मोड में हमने इसका असेसमेंट करा कि व्हाट इज द हाउ इज आवर पावर फ्लो स्ट्रेटजी इज गोना वर्क. तो इसमें कुछ पैरामीटर्स लिए गए. एक हमने पीवी मॉड्यूल लिया which is polycrystalline, has a maximum power at 1000 watt per meter square. Okay, it's a value of 250. Battery leads हमने which has a capacity of 20 ampere hour. Nominal voltage is 12 volt. Okay, let me zoom it for you. Just a second. I think it will be visible. Okay. फिर हमने number of batteries in series ली 2. एक अल्ट्रा कैपेसिटर मॉड्यूल लिया विच हैज अ रेटेड वोल्टेज ऑफ 16 वोल्ट, कैपेसिटेंस ऑफ 58 farad, and the maximum current it can allow which is 170 ampere. Then there is a DC link of the voltage 48 volt. Then there are loads which are essential loads and the non-essential. So basically we have to calculate the load in terms of the resistances. Then the 23 ohm non-essential is 46 ohm. Then the utility, which is grid, which is a single phase. It has a RMS voltage of 230 with a 50 hertz frequency. Okay, and the controllers which are attached to the battery for controlling the voltages and all that. For battery, we have taken the proportional constant value 0.3693. Then Ki, for integral constant, which is 80. Then for the ultra capacitors, we have used the proportional constant zero point 0.8. Then the integral is 202.67. For PV, we have taken the 1.5, and for I, the integral constant, which is 250. Then the outer voltage loop, we have taken this. Okay. So based on that, we have implemented the results. I would show it here. So what it does here, these are the results from the peak hour mode. Okay, so it shows the irradiance of what? Solar irradiance. I will zoom it for you. Just a second. Okay, so first it shows the variation for the irradiance. Then second graph is of the SOC of the battery. It is state of charge. How does it vary? It varies start from 60, then charges for the some cases 1, then for the case 2 is case 3 is the battery discharges. Then for the load shedding, battery also discharges because it is supplying the power energy. Then here is the third one is the DC bus voltage, which shows variation for various cases, case 2, case 1, case 3, and all those. Then comes the variation of the current for solar PV. For solar PV. Okay. So this is how all these variation goes like this. Okay. Now here in a peak hour mode, what are the conditions? Which I will write it here. So for a peak hour mode, various cases we have heard, case 1, case 2, case 3, case 4, and case 5. So various conditions are there which define these cases. For a case 1, the PPV means the generation of the power from the solar must be greater than the load, and SOC of the battery should be greater than 70%. Okay. and reference current is I reference of the grid should be equal to minus I LPVC, and I battery reference should be nearly equal to 0. And these work for the time instant T2 to T minus 3. Then another condition case here where we have taken the power of PV greater than P load and SOC of the battery less than 70%. Here I grid reference is nearly 0 and battery is equal to minus I LF PC. Okay, this correspond to the instant 0 to T2. Okay, then comes the T3. In this condition, we have taken PPV is less than PL and SOC of the battery should be greater than 30%. Okay, here the IG reference is nearly equal to 0 and then battery reference is equal to ILF PC. Okay, this is the third reference actually, and it corresponds to T3 to 12 seconds. This is the duration. Okay, then the last, which is you know PPV is still less than load, and SOCB is also less than 30% beyond the threshold. At that time, G reference will be equal to ILF PC and IB reference is equal to 0. And this corresponds to the time T5 to 12 seconds. So basically, I would show you here actually these. So these are the cases. Case 1 is here, which is T2 to T3, and 0 to T2 is the case 2. Okay. Then case 3 is T3 to 12 second. So T3 to 12 second here, and T5 to next is the case 4. So this will show how these are going to work. Okay. Then we analyze the same system for the off-peak hour, off-peak hour mode. Okay. Here we also have taken, four cases. What are those cases? Case 1 correspond when PPV is greater than P load and SOC of the battery is greater than 90%. Okay, off peak hour. Then what happens here is that IG reference will be equal to minus ILFPC and IB reference is equal to 0. Then another case is here PPV greater than PL and SOC is less than 90%. Okay, here IG reference is equal to 0 and I battery reference is minus ILF PC. This time correspond to T1 minus T2. This is the duration which will be corresponding to the 0 to T1. Okay. Then there is another case, case 3, where PPV is less than PL but SOC is greater than 60%. So therefore IG reference will be equal to 0 and IB reference will be equal to ILFPC. And this time will correspond to T2 minus T3 seconds. Okay. For another strategy is PPV is less than PL and SOC is less than 60. So at that time reference will be ILFPC and IB reference will be equal to 0. So basically, this will, this control strategy will help in maximizing what it does here. We simulated various patterns and how the energy is, energy of the battery or SOC of the battery is varying, which we have shown in the figures. So what it does here, that it will, this control strategy is proposed to, minimize the peak demand as well the optimal utilization of the renewable energy sources. Okay, and you can see from the results that you can see from the results the simulation results were satisfactory, and it helps the grid in the extreme conditions also. Okay, now we will go about another topic here, but before that I would like to solve some questions for you. Just a second. Okay, now we will discuss some of the things, how this, all these things happens in the, how we are, simulate these things. So actually, there are various hardware facilities I will show here in your figure. Just a second. कि किस तरीके से ये फैसिलिटीज जो हैं हम सिमुलेट करते हैं इन अ लेबोरेटरी. जस्ट अ सेकेंड. ओके. ओके, क्या है कि ये भी जो भी चीज हमने बनाई है, मतलब जो भी हमने सिमुलेटर्स, मैंने बताया था कि एक माइक्रो ग्रिड को हम व्हाट वेयर वी इम्प्लीमेंट ऑन द आरटीडीएस. तो इसके लिए एक लेबोरेटरी सेटअप होता है. ओके, which consists of various facilities, which consists of an RTDS, जो कि 6 racks हैं. Right side में you can clearly see there are 6 racks of RTDS, 1 2 3 4 5 6, and they have PV5 processors, and they can these RTDS can simulate 432 nodes. Okay, then we have some power amplifier. Why we use power amplifier? For the rated, they have a specification for the 5 kilovolt ampere continuous, see, and 10 kilowatt ampere short time peak power, and also 40 kilowatt ampere peak power. They also support power hardware in loop. Okay, and these power amplifier helps in the high accuracy of AC voltage and the current measurement, and they can also simulate or also support AC microgrid up to 270 VRMS in each phase. Okay, and they can perform the operation in four quadrant operation: zero lead, zero lag, and a unity power factor. The, then comes the PV emulator. What is a PV emulator? It is actually, what it does. It helps to emulate the working of a photovoltaic cell. So here you can see here 1 kilowatt PV panel is being shown here, which can implicate or imitate the practical source. It also helps to, it also can imitate the actual behavior. There is some shading effects can also be introduced, so that the practical, how the practical shading effect happen, it can also help in the imitation of that. Also, this PV emulator helps in the real world weather simulation, because in real world what happens sometimes, the irradiance increases, sometimes irradiance decreases, there is a temperature variance. So all those things can be emulated by this PV emulator. Then comes the wind emulator, which is it is driven by DFIG system, doubly fed induction generator. It is rotated. It is rated about 2.2 kilowatt. Okay, Then comes various sources. Real sources are also there. Hardware facilities in the lab, 1 kilowatt PV panels. Th- Then come the diesel generators, which are 3 kilowatt ampere, 230 volt, and 50 hertz single phase operation. Okay. Now comes the storage system, because if you want to to simulate the microgrid in any system, there will be requirement of various things like PV emulator, RTDS, and also wind emulators, and then the storage system. So here first one is a lead acid battery of capacity 60 ampere hour. Then come the ultra capacitor of 58 Ferret, and it can we can also add different type of storages if required. Okay, so it can help in investigation of if, all type of storages. Okay, just a second. Here there are various type of loads we can see, which are electronic loads are there to simulate. Electronic loads are there to simulate the all types of load, and their ratings vary per device from 1500 watt, and they may be constant power, constant impedance, or constant current loads. Whatever type of load we want to implement can also be implemented from these devices. Now comes the converters, which are they help in integration of sources, storage systems, and loads. There are various types of hardware facilities like AC to DC, DC to AC, DC to DC, and they have the bidirectional and a unidirectional capacity. Now comes the hardware in HIL. Actually, what happens here in HIL simulation, hardware devices are interfaced to the real-time simulator, and which contains rest of the module necessary to test the operation. Okay. It also HIS का क्या है? It also offers. I will write it down over here so you can easily you know help it. You can easily understand this. HIL क्या करता है? HIL. Okay. What it is? It is hardware in loop experimentation. Okay. I'm writing it down here so that you can take these notes. It will help in your examination also. So actually, what it does, it integrate or interface the real time simulators. Okay. Or actually, I will write it correctly. It will interface the hardware devices to real time simulators. Okay. These simulators are generally equipped models with models, so that testing of any operation, or I would say any simulation, can be carried out. तो इससे क्या होता है, कोई भी ऑपरेशन कोई भी तरीके का कैरीड आउट हो सकता है. लाइक आई हैव सेड दैट एक हमने माइक्रोग्रिड बनाया, उसको अगर हम रियल टाइम चेक करना चाहते हैं हाउ इट इज गोइंग टू हैपन, जो हमने केसेस बनाए थे, वो हम पूरी सारी चीजें जो है इस हार्डवेयर इन लूप एक्सपेरिमेंटेशन में लगा सकते हैं. ओके. और इसमें देयर आर two types of loop systems are there. One is closed, another is open. अब क्लोज लूप में क्या होता है? We already know feedback is given to real-time simulator. But in open loop, there is no feedback. Okay. So HIL simulations, I would say, are generally classified into control HIL, which is known as CHIL, then power HIL, which is PHI. Okay. अब इसमें CHIL में क्या होता है? कंट्रोल hardware in loop. Okay. What it does here in this, generally physical control or protection relay devices are interfaced, okay, with real time simulator. Okay, what it does, they allow the flow of digital or analog signal. Okay, there is another advantage of CHIL. It is that the signals can be extracted, I would say, can be exchanged at low voltage levels, which are generally plus minus, I would say, 10. This इससे क्या होता है कि लो वोल्टेज लेवल्स पे जब एक्सचेंज होता है, दिस विल क्या होता है, इससे दिस विल अलाउ अ डायरेक्ट इंटरफेसिंग of RTDS, of RTDS, real-time simulators using digital to analog or analog to digital converter. Okay, इससे ये फायदा होता है. तो क्या होता है, आई वुड एक तरीके का यहाँ पे एक ब्लॉक बनेगा विच इज रियल टाइम सिमुलेशन. ठीक है, ये एक ब्लॉक, ये जो है एक डिजिटल एनालॉग कन्वर्टर से कनेक्टेड है. डिजिटल एनालॉग सिग्नल्स यहाँ से जा रहे हैं, ये कनेक्टेड है एक एम्पलीफायर. ठीक, इट विल गिव द सिग्नल टू द डिवाइस, जो भी डिवाइस है, हार्डवेयर है अंडर सिमुलेशन, देन इट विल गिव इट बैक टू दिस. तो इस तरीके का एक लूप डेवलप हो गया, इंफॉर्मेशन इधर से फ्लो होगी इस तरीके से. तो This is how a hardware is integrated in the uh, this is how hardware is integrated to the CHIL. इसको हम कह सकते हैं schematic of CHIL simulation. ठीक. Then comes the PHIL. What is PHIL? Just told you about power hardware in loop. Okay. So what does PHIL does? It is actually helps in interfacing the power devices with RTS, with real-time simulator. Okay. So what happens here is power devices like, for example, power devices like motors, inverters, generators, and transformers. Okay. So basically, we can say the power exchange is done over PHIL interface. अगर हाई पावर हमको इंटरफेस चेंज करना है then it can be done over the PHIL. Okay. Now comes, so how does it interface? There is one real time simulation, then comes the scaling because the power is scaling. Then after that, any converter is applied. Then after that, it is amplified and it is given to the any power device which is under test. Then from there, voltage and current sensors will take the output. I would This will feed back to the digital to analog to digital converter through filters to the simulator. So this is how uh, power devices are interfaced using PHIL simulation. Okay. Now coming toward another topic here, which I would like to discuss. Just a second. A typical architecture of a typical architecture of DC microgrid. Okay, तो इसमें क्या है? I would quickly draw. This is a DC bus and this is a AC bus. Okay, this DC bus, there are smart loads which are DC in nature is connected. Okay, then comes the PV panels which are connected through boost converter to the DC bus. Then there are storages, battery, which is connected through DC to DC. I will draw it. Okay, and these are bidas. Then comes here a grid tied inverter. Just a second. Then comes here a point of a PCC which is connected to the grid. Okay, this is grid. This is PCC. What is PCC? Point of common coupling. Okay, these ACs are connected to the AC loads which are industrial, commercial also. Okay, so there are various switches which are connected. I will draw it here first. This is switch 2. Okay, just a second. It is point of common coupling. Okay, this is connected like this. Then here comes the another switch. So this is switch 2. This is switch 1. Okay, which is connected through an inductor. Let's say I would redraw it. This is connected to this and then a capacitor this here. Okay, now for an for an isolated system, the switch S1 is closed and S2 open. Okay, so for an isolated, this main grid must not be connected to the AC bus, so it will be open for isolated. What happens here? SW2 open and switch 1 is closed. Then only it will work like that. Okay. So basically, a DC microgrid can operate in three modes. First mode is grid tied. In a grid tied mode, switch S1 must be closed and S2 must also be closed. Okay. Then comes the islanded mode. Islanded mode. Okay. In an islanded mode, S1 must be closed and S2 open, like here. S2 must be open. Okay. Then there is another mode which is autonomous mode, which is autonomous mode. In that mode, S1 is open or S2 switch SW2 can be open or closed. In this mode of operation, it serves only the DC or AC loads in autonomous modes of operation. Okay. Now, what are the advantages of any DC microgrid? So, one of the most advantages of the DC microgrid, it helps in grid voltage and frequency support. Okay. It also helps in harmonic attenuation, harmonic suppression, I would say. Then it also helps in serving critical loads during grid outages. Then it helps in the energy management between a grid and a microgrid. It offers reliability, stability, and flexibility. Okay, these are some of the features of this uh, DC microgrid. So now on, we will be solving various questions which will help in better understanding of the topic. Okay, so question number one. Which component is critical for enabling the bi-directional energy flow in a smart grid? Okay, first is transformer, B, DC to DC converter, C. Energy meter. D. Circuit breaker. Write the answer in the chat box. Yes, B is the correct answer. B is the correct answer. Because I have shown you multiple times, whenever any battery it is connected to the DC bus, it is connected to the bidirectional converters. Okay, so B is the correct answer. What is happening? Just a second. Okay, okay. Question number two: energy management. Energy management allow, I would say, leads to first minimization of peak demand. Okay. Second, better integration of renewable energy sources. Third, leads to better grid support. Fourth, all of these. Okay, write that answer. Yes, D. Yes. Energy management, just like I've told you, it leads to the minimization of the peak demand and also leads to the better integration of renewable energy sources, and it's lead to the better grid support in terms of stability, all those things. And so correct answer is the all of these. Okay. Question number 3. Which of the following technologies is essential for implementing the demand response in a smart grid? First, phasor measurement units. B. Advanced metering infrastructure. C. Circuit breakers. D. Distribution transformer. Okay. Yes, phasor measurement units is not the correct answer. Circuit breaker is not. Distribution transformer. Advanced meter. Actually क्या होता है एडवांस मीटरिंग इंफ्रास्ट्रक्चर क्या करता है इट डिमांड रिस्पॉन्स एनालिसिस करता है ठीक है इससे ये पता चल सकता है हाउ मच एनर्जी वी कैन ट्रांसफर हाउ मच टाइम एंड ऑल दोज थिंग्स these are not, these all three does not support this. Okay, so question number 4. A bidirectional DC to DC converter can connect PV panels to a conventional three-phase grid. Then there is another statement. Ultracapacitors are connected to DC microgrid using an AC DC bidirectional converter. The first option is statement 1 and 2 both correct. B is statement first, second, both wrong. C, first correct, second wrong. D, First wrong. Second. So give me the correct answer. So, okay, okay, okay. Let's see. कौन सा सही है? A bidirectional DC converter can connect PV panels to a conventional three-phase grid. नहीं, ये सही नहीं. क्योंकि PV panels are connected to a by using DC-DC converter which are not bidirectional because energy can only flow from PV panels to the DC bus. Okay. Ultra capacitors are connected to the DC microgrid using an AC-DC node. They are connected through a DC-DC single edge bridge. Okay, directional convert. So दोनों ही statement गलत हैं. So from here we can say B is the correct answer. Question number 5. The AC-DC distribution system is more complex than a pure AC distribution system. Okay, A. Just a second. The AC-DC distribution system has fewer elements. C. Available load flow methods for transmission system can also be applied to AC-DC system. Okay. D here, all are correct. E here, all are incorrect. Okay. लेट्स सी। जी, क्या है? एसी डीसी सिस्टम इज मोर कॉम्प्लेक्स देन अ प्योर एसी डिस्ट्रीब्यूशन सिस्टम। यस, इट इज राइट। क्यों? क्योंकि एसी डीसी सिस्टम में बहुत ज्यादा कन्वर्टर्स आ जाते हैं। आपको क्या कहते हैं, डीसी कोई सिस्टम डीसी सोर्स है उसको डीसी डीसी बाई डायरेक्शनल कन्वर्टर या सिंगल डायरेक्शनल कन्वर्टर यानी बूस्ट कन्वर्टर से कनेक्ट करना पड़ता है। फिर उसके बाद हमें उसको एसी डीसी कन्वर्जन करना है। बहुत सारा सिस्टम जो है कॉम्प्लेक्स हो जाता है। सेकेंड ऑप्शन से द एसी डीसी डिस्ट्रीब्यूशन सिस्टम हैज fewer elements। नहीं, इट इज द रॉन्ग थिंग। Available load flow methods for transmission system can also be applied to AC-DC system. No, we cannot apply the methods to the transmission system to the AC-DC method system, microgrid. So, correct statement is this one. Question number 6. What are the main features of power flow control strategy in energy management system? पहला ऑप्शन peak load reduction, B. Effective control and management, C. Increase in the lifespan of energy storage system, D. All of the above. Yes. पावर कंट्रोल स्ट्रेटजी इसलिए लगाई जाती है ताकि हम पीक लोड रिडक्शन कर सकें, और देयर इज इफेक्टिव कंट्रोल and management of various sources and load so that the effective utilization of available generation can be done. It also helps in the increase in the lifespan of an energy storage system. The reason behind this, it will not lead to overcharge and a discharge of the energy storage system. So that's why the correct answer will be D, which is all of the above. ठीक है? तो एनर्जी सिस्टम को क्या होता है कि ये चार्जिंग ज़्यादा चार्ज भी नहीं करने देता, ओवर चार्ज भी नहीं करने देता, और डीप डिस्चार्ज भी नहीं करने देता, जिसकी वजह से इट लाइफ स्पैन ऑफ द एनर्जी सिस्टम इंक्रीज करता है। नो आइडिया व्हाट्स हैपनिंग। क्वेश्चन नंबर 7। रिन्यूएबल generation is highly promoted in the country due increase in per capita consumption, B. Deficiency of fossil fuels. C. Both. D. None. I think you should know the answer. C. Yes. So C. कंजप्शन इंक्रीज हो रहा है तो इस वजह से रिन्यूएबल जनरेशन इज अ यू नो इफेक्टिव energy source, or fossil fuels are also getting depleted day by day, year by year. So we are moving toward a renewable energy centric generation. So C is the correct answer. Next question is question number 8. Identify correct statement. Okay, first, in PHIL applications, the control signals are of high voltage level. B. In CHIL application, the control signals are of low voltage level. C. In PHIL, the of circuit is complexity of the circuit is more than of CHIL. D. Both. B and C. E. Both. A and B. ठीक. So give me the correct answer. Okay. Anyone else? In PHIL application, the control signal are of high voltage. It is wrong. Yes, we are, in PHIL application, जो control voltages होते हैं, जो power devices होती हैं, they are hardware जो होता है वो power devices होती हैं. But after that, there is, उनका voltage level down किया जाता है. But in CHIL application, the control signals are low voltage, which is right. और ड्यू टू दैट वोल्टेज लेवल को डाउन करने की वजह से complexity of the PHIL becomes more because there are more number of devices gets add up. So that's why. और इन CHIL क्या होता है डायरेक्ट इंटीग्रेशन हो जाता है स्ट्रेट फॉरवर्ड इंटीग्रेशन ऑफ अ हार्डवेयर टू द RDD. So basically B and C are correct. So D is the correct answer. Question number 9. Which of the following are the challenges of AC DC load flow analysis? Okay, पहला है require proper modeling of various power converters in the load flow equation. B requires modeling of storage and various DC loads. Okay, modeling of various type of distributed energy sources like PV system, geothermal, wind. D all of the above. Which is the correct answer? Yes. ये सब चैलेंजेस हैं कि पावर कन्वर्टर्स की मॉडलिंग कैसी होनी चाहिए, इक्वेशन में स्टोरेजेस कैसे मॉडल करने चाहिए, वेरियस वेरियस डीआर जो होते हैं उन सबकी मॉडलिंग क्या होनी चाहिए. तो क्वेश्चन नंबर 9. क्वेश्चन नंबर 10. AC load flow studies refers to transient state analysis of power system. Okay. Then low AC load flow computes the voltage and angle at each bus. ओके, तो इसमें से कौन सा ऑप्शन करेक्ट है? फर्स्ट, ए एंड बी बोथ. सेकंड, ए रॉन्ग, बी करेक्ट. थर्ड, ए करेक्ट, बी रॉन्ग. So give me the answer. AC load flow studies refers to the transient steady state analysis of the power system, computing voltages and angle at each bus. Then AC load flow computes the low voltage angle at each bus. तो क्या होता है, ट्रांजिएंट एनालिसिस तो अलग से करना होता है, ठीक है. तो इसी वजह से एसी लोड फ्लो ट्रांजिएंट एनालिसिस नहीं करता. इससे रॉन्ग, दिस इज राइट. So second is the correct answer. I don't know why this slide is coming again and again and again. Which of the methods are suitable for distribution system means low x by r. Okay. First A, Newton Raphson. B, Gauss Seidel. C, direct load flow based on BIBC and BIBV. C, both B and D, both B and C. So give me the correct answer. अब देखो क्या है इसमें, डिस्ट्रीब्यूशन सिस्टम्स के जो x by r रेशियो होता है इज वेरी लो, so they are more resistive. Due to that, Newton-Raphson is not a suitable. Same goes for the Gauss-Seidel. But direct load flow, which is based on the BIVC, is a much more suitable for the distribution system. Reason behind this is because they have a low x by r ratio. But on the other hand, transmission systems has high x by r ratio. So therefore, Newton-Raphson and Gauss-Seidel methods are more suitable for the transmission system, load flow analysis for the transmission system. The reason behind this is they have a high x by r ratio. But for the distribution system, we have direct load flow. There is another load flow method which is forward, backward, sweep method. Okay, I will write it down in correct way. Forward, backward, sweep method. This is also used for the radial systems which have a low x by r ratio. Okay, so I hope you have enjoyed it here, and thank you for your coming. And I hope you have get the hold of the concept behind this. Okay, and if you have any question regarding this, you can ask me right now. Otherwise, you are good to go. Thank you. Thank you.